Welcome you all for this lecture series on deep learning. In this lecture, we'll see RNN design patterns. In that, we'll briefly discuss about the topics acceptor, encoder, and transducer. We'll see one by one. First, the RNN design pattern, the introduction about RNN design patterns. This RNN process sequential data using a recurrent hidden state. This we have seen it in the previous lecture. The recurrent neural networks, RNNs, are designed to handle sequential data by maintaining a hidden state that carries information from previous time steps. This hidden state acts as a memory, enabling the network to model temporal dependencies present in sequences such as text, speech, or signal. And different tasks require different input output structures. We'll see the example for this cases also. Depending on the problem, an RNN may need to produce a single output, a sequence of outputs, or a fixed length representations. Therefore, the same RNN architecture is adopted into different structural patterns to suit the task requirements based on the applications we are going to take into account. And these structures are called the RNN design patterns. RNN design patterns define how inputs and outputs are organized across time steps. They specify when outputs are generated and how the final decision is made based on the hidden states. And the important patterns are acceptor, encoder, and transducer. The most commonly used RNN design patterns are the acceptor, encoder, and the transducer patterns, each serving a distinct purpose. Each will have their own merits and demerits and their applications, and each will be serving as a distinct purpose in sequence modeling tasks. Next, basic RNN equations. The hidden equation is given by hidden state update equation as given by H t is equal to function of, this is the activation function, Wxxt plus Wh minus 1 plus Bh. The hidden state at time t is computed using the current input and the previous hidden states. So this is given by this equation. This allows the RNN to retain past information while incorporating new inputs and output. There is new inputs in each time step. And the output equation is given by, when the output is required, it is computed from the hidden state. It is equal to G of, this is the activation function, Wht plus By. This maps the hidden representation to the desired output space, such as class probabilities or numerical values. So here the xt is input, ht is the hidden state, and f of dot, this is the activation function. This may be a ReLU or a tanh. G of h is the softmax or a sigmoidal function. So we'll be going for if you are going for the classifications. Next, so outputs, so in this case, the output is produced by this equation. Only at the final time step, the intermediate steps are, we are going to use it. Hidden states are computed but ignored for the predictions. So only the final hidden state is used to generate the output and ensuring the decisions. Next, and here this, and also you should know this pattern is ideal for tasks where the entire sequence determines the label, such as sentiment analysis or signal classifications. Next, RNN design patterns using the acceptors. So it has been given by sequences. In this case, sequence we are taking, and one entire sequence will be taking. In this, we are going to extract only the single output, and output is produced only at the final time step, and it is used for the sequence level classification. So the equation is given by input sequence equation is given by represented by input sequences are given by x1 x2 up to xt, and the hidden states are given by function of wx and xt plus up to wh h of t minus 1, where the temporal order is important for correct interpretation. And next, the hidden state computation. This is the hidden state computation is given by this equation, it allowing the RNN to accumulate information over time. And the final output This is the final output equation. The final output is generated using y is equal to g of wy into g of wy ht. This is the activation function. This will summarize the entire input equation. From this, the loss function is given by the training objective is defined as L is equal to L of y comma y target, which measures the difference between the predicted and the true label. This is predicted and true labels. And if you are coming into the applications of the application, that is acceptors, this is main used in the sentiment analysis, ECG, EEG signal classification, the spam. So ECG or ECG signal classification, spam detection, and language identification, where one final decision must be made after observing the full sequence. So, for example, the read a full sequence, then decide once. That means, I'll tell you one best example. The acceptor pattern reads the entire input sequence. For example, this may be how many words, that is not a my. So it will read the entire input sequence first, and then produces one final output using the last hidden state. That means read the full sequence, then decide the once means last hidden states. So if you are taking one harmonized example, I read a full movie review from start to end. On full movie I am taking, I'll go for the review from start to end. Only after finishing reading, I decide whether the review is positive or negative. I don't decide after each sentence. I decide once at an end. And the real world examples are the sentiment analysis and ECG signal classification, whether it is normal or after going through all the tests, finally we are going for only one output, whether it is a normal case or the abnormal case. Next type is the RNN design pattern encoder. And here the sequence is the fixed length vector. The encoder pattern transforms the variable length input sequence into a fixed dimensional vector representation. Here, the no output during the intermediate step means, unlike the transducer, the encoder does not generate output at each time. It focuses solely on building an internal representation. And the final hidden state represents the entire sequence. The final hidden state captures the that is semantic or temporal information of the entire input sequences. And the encoder equation is given by the hidden state is updated at each time step using ht is equal to f of wx plus into xt plus wh into h of t minus 1, ensuring the cumulative learning across the sequences. And the context vector is given by the context vector is given by the encoder representation is given by c is equal to h suffix t, which acts as a compressed summary of the input. And here C is passed to the decoder or the classifier. Now, the applications of the encoder is it is used in the machine translation, text summarization, speech recognition, image capturing, and here it compresses sequence to a single vector. I'll tell you one example for this. Mainly encoder pattern, the sequence to here. So the encoder pattern is reads the sequence and compresses all the information into a single fixed length vector called a context vector. That means compresses a sequence into a single vector. The real world example, if suppose if you are listening to a long lecture, one long lecture up to 1 hour or 2 hour or 3 hours, and then I write a short notes that captures the entire lecture in a few key point. Those notes represents the whole lecture. For example, if I am listening 1 hour lecture, I am taking the notes, and short notes I am taking. That short notes may be telling about that 1 hour lecture. The real world examples, as I've said, machine translation, input sequence encoding, text summarization, image captioning. That means CNN captioning. In this case, CNN plus RNN encoders are used. The next type is the RNN design pattern is the transducer. It is in this case the sequence being converted into a sequence. That means the transducer pattern maps an input sequence to an output sequence of the same length. Output generated at every time step. Each input element produces the corresponding output, making the pattern suitable for time aligned tasks. And input and output lengths are here equal. This one-to-one temporal mapping ensures distinct correspondence between the input and output sequences. And here the equations are given by the hidden state equation is computed as ht is equal to f of wxxt plus wh h of t1 as like previous. The output at each stem is given by yt into g of wyht. This is the g is the activation function. This preserves the temporal continuity, and the output equation is given by this equation. And finally the loss function, the overall loss function is given by here the summation will come L is equal to summation of t is equal to 1 to t L of yt comma y of t target, which accumulates the error across all time steps. So the applications of the transducers are these are all the applications. The transduction pattern is used in speech recognition, part of speech tagging, time series forecasting, and signal processing where continuous output is required. So in this case, what it does sequence to sequence, what it does mean the transducer pattern produces an output at every time step while reading the input, and the input and output evolve together in a time. Suppose if I listen to someone speaking in English, and I translate each word immediately into another language while they are speaking. For example, what's your name? If I am speaking in English, immediately it will be translated to whatever the language is required. So the real world, so that means whatever the input you are giving, the same output you are going to get it. So if I am listening speaking in English, if I wanted the same English language is being translated into Tamil or Hindi or any other languages, it will be immediately translated into another language while they are speaking, and input and output happen together in time. The real world applications of speech recognition, part of speech tagging, and time series predictions. Coming into the comparisons, so here the acceptor uses the accept here the acceptor uses the sequence to one sequence, and it is being given by the output equation g of wi into hi. The acceptor uses the final hidden state for a single output. The encoder produces a fixed length context vector, and the transducer generates the output at every time step sequence to sequence. Their equations clearly reflect these structural differences. And finally, coming into the summary, acceptor summary, acceptor produces a single output using this equation g of wi, that is g of this is the activation function wi into ht, and is suited for sequence level decisions. And the encoder compresses the entire sequence c is equal to ht, which serves as a context representation, and the transducer, it will produces each time step, and it has been given by what yt is equal to g of wi into ht. A simple way to remember how you are going to remember this RNN design pattern is to relate them to how humans naturally process information. So in the acceptor pattern, the model reads the entire the model so as I've said, a model reads the everything and then decides once, just like how I read an entire movie review or a medical report before giving the final opinion. So the RNN process all time steps stores the information in its hidden state and uses only the final hidden state to make the single decision. So the encoder model reads everything and summarizes, similar to how I listen to a long lecture and then write short notes that captures the main ideas. Here the RNN converts the whole input sequence into compact fixed length vector that represents the entire sequence. So in transducer, what it will do pattern, the model reads and responds together, just like how I translate speech word by word while listening or take live notes during lecture. So the RNN produces an output at every time step, ensuring continuous time aligned responses. So this memory trick helps clearly understand when outputs are generated and how sequences are processed in different RNN applications. So this is the humanized example for this. Acceptor, what it will do, it will read everything and decide once. Read a full movie review and it will be giving only one answer, and it will be encoder read everything and summarize entire lecture, 2 hours 3 hours lecture, and will be taking a short notes. Transducer If suppose if I want to have the translation from English to Hindi or Hindi to English or any other language, immediately I can able to translate it. This is the difference between acceptor, encoder, and transducer. Entire full movie read full movie, and I am going to give one answer. And the entire lecture, I'll be 2 to 3 hours lecture. I'll be listening. I'll be taking a short notes about the 2 to 3 hours lecture. Here, if I want to have the translation or anything machine translation, immediately I can be able to do it. I suppose if I'm talking in one language, if immediately I wanted to know the another language or my mother tongue, I can be able to translate it. Each and every word can be translated into. So these are all the difference between the design patterns of RNN, acceptor, encoder, and transducer. Hope everyone understood about these the design patterns of RNNs. The types are acceptor, encoder, and transducer. So the remaining things we'll discuss in the next lecture. Thank you.